Hey, welcome back, guys. This is going to be for Physics C students. We're through the content, and all we need to do is go back and add in some derivations and some calculus, and it'll be good for the exam. We're going to start at the beginning, which is going to be kinematics. Kinematics is going to be 18% of your test, and we'll try to go through and review and add in calculus as useful. I give you the notes as well as what our objectives are. All right, so we're going to start with position and displacement. Position is going to be where something's located in. Displacement is going to be a vector that represents the difference between where it started and where it ended up. When we see a delta in front of something, we take the final position minus the initial position. This is going to be a vector quantity, which means it's going to have both magnitude and direction. The magnitude is just how long the arrow is. The direction will be the direction that the arrow points. And we're going to take up to be positive, down to be negative, to the right to be positive, and to the left to be negative. There's a difference between distance and displacement. Here we have someone walking along a curved line there. Their distance, which would be the length in purple that they went, would be much different than the displacement, which only takes into account where you end up and where you start. And this is in our previous notes as well. We can see here that someone that went east for 70 meters and then west for 30 meters would have a displacement of 40 meters east, but the distance they would have traveled would have been 100. Once we have distance and displacement, we can talk about speed and velocity. Velocity is going to be a vector, very much like displacement, and velocity is going to be our change in displacement over time. Speed is going to be a scalar, and this is going to be our change in distance over time. Average speed is our total distance over total time, and that doesn't mean that at any point that that's our speed for all of the time, just our average. Units for this would be meters per second. Graphs are important in this, position time graphs. Always in physics, the first thing listed is our y-axis. The second thing listed is our x-axis. The slope of this line will give us our velocity. If you take a tangent line and a curve, it'll also give you the velocity. A curved line tells us we have acceleration. This is not necessarily constant acceleration. It's hard for us to tell from a curved line whether it's constant acceleration or a changing acceleration. All right, so in general, our velocity at an instant is going to be the change in displacement over time as time goes to zero, which we call the derivative of displacement over time. When we're talking about velocity in our text, we're talking about instantaneous velocity unless they tell you it's average velocity. And we can find this by looking at our slope at that given point. So here we have a curve, and we've seen this in LogaPro in the labs where there's a tangent tool. You guys will do it in the little Brother Charles lab. And you can trace along the line at every given point. It'll tell you what the slope is at that given point because it's changing throughout. Physically, it's hard to do this. It's hard to draw a tangent line to a curve and get a very accurate slope, as you can imagine. Even drawing a best fit line for a linear thing, our slopes are going to be a large source of error. Average acceleration is going to be our change in velocity over time. And if our acceleration is to the right or up or forward, it's going to be positive acceleration. And if it's to the left or down or backwards, it's going to be negative acceleration. Acceleration is always in the same direction as net force. The velocity does not have to agree or disagree with the direction of the acceleration. Acceleration tells us how our velocity is going to change. If something's slowing down, we call that deceleration. It's not necessarily negative acceleration. The units for this are going to be meters per second or meters per second squared. And this is going to be the first derivative of velocity with respect to time, or the second derivative of position with respect to time. So these are equivalents. As well, you can see them written as v prime, x double prime, and sometimes you'll see a dot on top. These mean exactly the same things in calculus, depending on what notation you use. All right, so a particle's position on the x-axis is given by 4 minus 27t plus t cubed. Find the velocity function. So I'm going to take the derivative of x with respect to t, and this is going to give me negative 27 plus 3t squared. Is going to be equal to my velocity. Is the velocity ever zero? So can I set this equal to 0? And I'm going to get that 3t squared equals 27. So t squared is going to be equal to 9. So t would be plus or minus 3. And so yes, at 3 seconds it would be 0. Our acceleration function would be the derivative of the velocity function with respect to time. And this is going to be 6t. This is a problem from the AP exam. The velocity of a particle is moving along the x-axis is given as a function of time by the expression v of t equals 3t squared minus 2t plus 4, where v is in meters per second and t is in seconds. What is the acceleration of the particle at t equals 2 seconds? And again, this is what's given to you on your equation sheets. You're not only given the physics equations, but they give you the calculus that you need to solve. You just need to know how to use it. And so when we take the derivative of x to a power of n, this is equal to n times x to the power of n minus 1. So applying this to my velocity, I get that my acceleration is 6t, because I would have 2 times 3, which is 6, then 2 minus 1 would be 1, minus 2. So t to the first, so 1 times 2 would be 2, and then 1 minus 1 would be 0. T to the 0 is just 1, and then the derivative of this would be 0. So our acceleration would be 6t minus 2, and this would be 6 times 2 minus 2, which would give me a choice of d. And I realize this would be easier for you guys to read off of the paper I gave you, and hopefully you're working along with this. An object moving in a straight line has a velocity v in meters per second that varies with time t in seconds according to the following function. V equals 4 plus 0.5 t squared, the instantaneous acceleration of the object at t equals 2 seconds. So again, using our quotient rule, my acceleration is going to be equal to 0.5 times 2, which is 1. So it is going to be just t. And so if I put in a 2, I'm just going to get 2 meters per second. The displacement of an object between t equals 0 and t equals 6 seconds. All right, so just like you guys have learned that you can take a derivative to go from displacement to velocity to acceleration, you can go in the opposite direction, which you've learned as an antiderivative or an integral. This is our symbol for our integral, and the integral of x to n dx is going to be equal to 1 over n plus 1 x to the n plus 1 power, as long as n doesn't equal to negative 1. And we'll get into that. We'll have examples where n is equal to that. So we want to take the derivative of velocity with respect to time, and this is going to give us our x. And so I would write this as 0 to 6 of 4 plus 0.5 t squared dt. And you guys are going to be a lot more particular with your notation than I am. And so this would be 4t plus t cubed. I need to cancel out a 3 when I go down, and so this is going to be 0.5 over 3, which I can rewrite as 4 plus 1 over 6 t cubed. And then to check this, I could take a derivative and make sure that I get the same thing. And so if I took the derivative of this with respect to t, my 4t would become 4. My pluses kind of look like t's, it's a little confusing. And the derivative of this would be t squared times 1/2. All right, so 0 is going to be 0, so I'm just going to have to put in a 6. And I got 60. All right, we can also have velocity time graphs. These are useful. If we take the slope, we get the acceleration. If we take the area under it, whether it is just rectangles or triangles, or if you have to take the integral of the function, which also we've seen in Logopro, take an integral of the function, we can get what the area is, which will give us our distance or our displacement. If all of our values are positive, need a drink of water. Our distance and our displacement will agree. If some of the velocities are positive and negative, our distance and displacement will be different. All right, so from a velocity time graph, our slope is going to be our acceleration. The area is going to be distance or displacement. For a position time graph, our slope is going to be the instantaneous velocity. A curved line tells us that we have some kind of acceleration. It does not need to be constant acceleration. It could be a changing acceleration. So around the surface of the Earth, we have near constant acceleration. So unless they tell you that you're not on Earth, you can assume that your acceleration is going to be g. G hovers around 9.8, but it varies on different places on the Earth. I know in calculus you guys use 32 feet per second. You can use 9.8. For a large portion of the time that the AP test existed, you weren't allowed to use a calculator or an equation sheet on multiple choice. That's not the case anymore. But because of that, that's where we get the assumption that G is about 10. And that made the math a lot easier for students to deal with, because dividing by 10 Multiplying by 10 is just a matter of moving a decimal point. All right, so as we leave the surface of the Earth, and this is a chart goes up in terms of kilometers, we can see that the acceleration will slowly decrease as we get far away. We can see that this is curved, and that is because our acceleration is inversely related to the radius squared, which would be the distance from the center of mass of Earth, which we can consider to be the center of it. All right, so on your equation sheet, here's our G is 9.8. This is what it looks like on the first page of yours. All right, so if an object falls only under the motion of gravity, it's going to be in free fall. If air resistance is present, it won't be. And we're going to spend at least a week, maybe more, on, they're big on air resistance problems in AP. But I'm going to wait a little bit to make sure you guys have gotten it, because the last I asked, you guys hadn't done natural log stuff. So near the surface of the Earth, everything experiences the same amount of acceleration, and if we disregard air resistance, everything is going to reach the ground at the same time. This happens really fast, and that's why inclines and Atwood machines are integral parts of us studying physics, because it allows us to slow down the effects of gravity and actually measure what they are. I did this demonstration for you, I think, or I told you about it, but they're dropping a ball on a paper, and the ball obviously goes down because air resistance has a big effect on the paper, but you could crumple up the paper and those two would fall at the same rate. As soon as you let go of something, it's important to note that acceleration is -10. So gravity acts at the speed of light. One of the things that we get from Einstein. So as soon as you let go, it goes right to -10. Our velocity is at rest, our position's at rest, and we can see that our velocity is changing by 10 meters per second every second, whereas our position is changing by 5, then 15, then 25, then 35. So this is one of the things that Galileo noticed studying this, that we had this increment of how gravity affects things. And it would work on an incline too. So the distance it went the first distance down the incline, it would be triple in the second, and it would be quintuple, maybe? I don't know what 5 times is actually called. And again, here's something going up and going down. Again, -10 makes it easy for us, because if I throw something up at 40 meters per second, it's going to get to the highest point at 4 seconds. That's how long it would take to cancel out 40 meters per second. It's going to take another 4 seconds to get down. So I know it's going to be 8 seconds without doing any math. And again, you guys need to be able to do 35 multiple choice questions in 45 minutes. So any ones you can do like that is going to be helpful, because we're going to see some of the multiple choice questions take some time. Here are our equations. These are only for constant acceleration. And here is how they appear on your equation sheet. As Vx equals Vx naught plus Axt, x equals x naught. I moved the x naught to the other side for my convenience, is equal to Vx naught t plus 1/2 Axt squared. Vx squared equals Vx naught squared plus 2Ax x minus x naught. It's hard to say when they're adding all those extra x's in there.